right, so there's a note here. We're on bottom of page 14. Note on the content of this section, multiple linear regression. We're in chapter 11. So the original version of this PDF textbook, the original version goes into great detail on the topic of multiple linear regression, including advanced mathematical formulas. This is the revised version that we're looking at now, which includes a much more abbreviated introduction to multiple linear regression. But if you are looking for a more advanced reading, definitely go review the original textbook chapter. So the simple linear regression model that we've discussed up to this point, it assumes that there's a single predictor variable, okay? So it assumes that there's a single predictor variable that you're interested in, and in that case it was the sleep variable, okay? Now, in fact, up to this point, every statistical tool that this author has talked about has assumed that your analysis is going to use one predictor variable and one outcome variable. But in many research projects, most of them, you actually have multiple predictors that you want to examine. And if so, it would be nice to be able to extend the linear regression framework to be able to include multiple predictors. Perhaps some kind of multiple regression model would then be in order. So multiple regression is conceptually very simple. All we do is add more terms to our regression equation. Let's suppose that we've got two variables that we're interested in, okay? Perhaps we want to use Danny's sleep and baby's sleep to predict Danny's grumpiness, okay? So as before, we can let y subscript I refer to Danny's grumpiness on the ith day. Now we have two x variables, the first corresponding to the amount of sleep that Danny gets, and the second corresponding to the amount of sleep that the baby gets. So we're going to let x subscript I1 refer to the hours of sleep Danny got on the ith day, and x subscript I2 refer to the hours that the baby slept on that day. So then we're going to write this regression model equation on page 15. All right, so y subscript I equals beta 0 plus beta 1 xi1 plus beta 2 xi2 plus epsilon I. So as before, epsilon I is your residual that's associated with the ith observation. And the EI, right, the epsilon I, equals y subscript I minus estimated y subscript I. In this model, we now have three coefficients that need to be estimated. So b subscript 0 is the intercept. B subscript 1 is the coefficient associated with Danny's sleep, and B subscript 2 is the coefficient associated with the baby's sleep. So however, although the number of coefficients that need to be estimated has changed, the basic idea of how the estimation works has not changed. So our estimated coefficients of approximated beta 0, approximated beta 1, and approximated or estimated beta 2 are those that minimize the sum squared residuals. So now we're going to look at what are the assumptions of the multiple linear regression. So multiple linear regression has the same four assumptions as simple linear regression. So we just went over this, but there is one additional assumption called multi-collinearity. This happens when two or more independent variables in a multiple regression model are highly correlated with each other. This means that they provide similar information about the relationship with the dependent variable. So here's an example. Imagine you're trying to understand how both the amount of time spent studying and the number of practice tests taken can affect your test score. So if the time spent studying and the number of practice tests are closely related, because more studying often means more practice tests, it becomes hard to tell which one is really influencing the test score. So when multi-collinearity is presented, it can make the results of your regression analysis seem confusing. The coefficients, which are the numbers that show the relationship between each independent variable and the dependent variable, can become unstable and hard to interpret. This can lead to misleading conclusions about which variables are actually important. So to sum it up, multi-collinearity, it makes it difficult to understand the true impact of each independent variable on the dependent variable. So it's like trying to listen to two people talking at the same time. It's kind of hard to figure out who is actually saying what, and what to focus on, right? So let's move into 11.5.2. We're on page 15. So how do we interpret the multiple linear regression output? Okay, so as we mentioned earlier, we're not going to delve into every detail of multiple linear regression. It's beyond the scope of an introductory lesson. So instead of getting into the complex mathematics, we're going to focus on how to interpret the different values that you're going to encounter in published research articles. So the output that is seen in figure 11.14 was obtained using JASP. Multiple regression in JASP is no different to simple regression. So all we have to do is add additional variables to the covariate box. So for example, if we want to use Danny's sleep and baby's sleep as predictors in our attempt to explain the grumpiness, then we'll move baby's sleep into the covariate box alongside with Danny's sleep. So let's walk through each of the three tables that is going to be provided by default in JASP, and then we'll point out the values that you're most likely to see featured in research articles. So hold on. So we go regression, linear regression. We're going to move Danny's sleep and baby's sleep. Oops, sorry. We're going to move grumpiness here. And then we're going to move Danny's sleep and baby's sleep to covariates. Okay. So again, let's make sure we did that right. So we're we're interpreting multiple linear regression output, and we moved our Danny's sleep and our baby's sleep to the covariates box, okay? And then we have grumpiness in the dependent variable. So we're at the bottom of page 15, about to jump into 16. So the model summary table, okay, that table at the top, It has Danny Grump there. This title reminds us that the dependent variable for these analysis is grumpiness. So as we saw with this simple linear regression, the top row is still labeled M subscript 0 and represents the null model. Yep. The null model only includes the y-intercept. And it has no independent variables. Okay. Moving to page 16, let's double check. So we have our 000, 0.903, 0.816, 0.812, 4.354, and 10.050. We have our ANOVA in the middle, 8160, 1839, 99.99, 297 and 99, 4079.95, 18.96, 215.2, p-value 0.001, and then we have our coefficients at the bottom, 63.710, 125.966, negative 8.95, 1.005, 3.041, 0.553, 0.271, 0.905 negative, and T is 63.395, and then 41.423, negative 16.172, 0.039. We have our p-values, so less than 0.001 is recorded 3 times, and then in the very bottom is 0.969 for baby sleep. All right, so let's go through this. So we are on page 16. We already consulted figure 11.14, which is our JASP output for multiple linear regression model, and it matches what we got, so that's great. So again, the second row is labeled M1. This is our model. If we look down to the coefficients table, we can see that M1 includes the y-intercept and Danny sleep and baby sleep. Okay. The values on the model summary table that you're most likely to see, again, are the R squared and the adjusted R squared. R squared is your same coefficient of determination that we saw with the Pearson's R and the simple linear regression, but now it's looking at the relationship between all of the independent variables together and the dependent variable. So it measures how well the independent variables explain the variability of the dependent variable. It's a popular measure of effect size because it's relatively easy to interpret. So in a simple linear regression model, R squared can be computed with this formula. So 1 minus SS residual divided by SS total, okay? And that is your R squared. So again, in this formula, we have SS residual is the sum of square residuals, okay? And the SS total is the sum of square total. Both of these can be found in your ANOVA table. So sum of squares, residual, okay, the 1839 divided by your total, which is 99.99, which gives you 1 minus 0.183, which equals 0.816, and here's your R squared, so that's right. So to interpret this, you multiply the 0.816 by 100. So this says that 81.6% of the variability in Danny's grumpiness can be explained by the variation in how many hours of sleep they got and how many hours of sleep the baby got. We're at the bottom of page 16, so now that we're dealing with regression models with multiple independent variables, it is important to note that adding more independent variables hold on, let's go back. So now that we're dealing with regression models with multiple independent variables, it is important to note that adding more independent variables to your model will generally improve its predictive ability, or at least not negatively impact it. So we're on page 17. In other words, as we add more variables, R squared tends to increase. So if a useless variable is added, then the R squared will not change. So however, adding a variable should never cause R squared to decrease. To avoid an inflated R squared value, we sometimes use the adjusted R squared value, okay? So 0.816 versus 0.812, it's pretty close. The adjusted R squared value introduces a slight change to your calculation, and so we can see that for a regression model with k independent variables fit to a data set containing n observations, the adjusted R is this equation. Okay, so it's the SS residual divided by SS total times n minus 1 over n minus k minus 1, and then you take that and you do 1 minus that will give you your R squared. So plugging in these values, we have 100 minus 1 because we have n number of values, and then in the denominator 100 minus 2 minus 1, okay, and then so we have that comes out to 1.021, multiply that times the 0.184, and then 1 minus that equals 0.812. This adjustment is an attempt to take the degrees of freedom into account. The big advantage of the adjusted R squared value is that when you add more predictors to your model, the adjusted R squared value will only increase if the new variable improves if the new variables improve the model performance more than you'd expect by chance. So let's say that again. So this adjustment in R squared, it's an attempt to take your degrees of freedom into account. The big advantage of the R squared value is that when you add more predictors to the model, the adjusted R squared value will only increase if the new variables added improve the model's performance more than you actually expected originally, okay, or more than you'd expect by just pure chance. So the big disadvantage is that the adjusted R squared value can't be interpreted in the elegant way that the R squared can. The R squared has a simple interpretation as the proportion of variance in the outcome variable that is explained by the regression model. So let's say that again. R squared, right? It has a simple interpretation as the proportion of the variance in the outcome variable that is explained by the regression model. To the author's knowledge, no equivalent interpretation exists for the adjusted R squared. So an obvious question then is whether you should report R squared or the adjusted R squared. This is a matter of personal preference. If you prioritize interpretability, then the R squared would be more suitable. On the other hand, if you are concerned about correcting for bias, then the adjusted R squared is better. Personally, the author prefers R squared because they believe it's more important to interpret your measure of model performance. However, be aware that if a study includes many variables in its model, this may inflate the value of R squared. Now, with our ANOVA table, which is our second figure, right? We have our model summary, our ANOVA, and our coefficients. So just as we saw with the simple linear regression, this ANOVA table is addressing the statistical significance of the overall model. So in this case, it's looking at whether the model containing both Danny's sleep and baby's sleep can predict the grumpiness. The null hypothesis is that the model does not predict the grumpiness. The alternative hypothesis is that the model does. Okay? So the p-value on this table is used to test for the statistical significance of the model. In this example, with p less than 0.001, this tells us to reject the null hypothesis. So I see that. These results are statistically significant. There is evidence that this model can be used to predict grumpiness in the population. If you're reading a research article, you might see the F-test statistic also reported, along with degree of freedom and the p-value. So to write that in APA style, the common format would be F and then parentheses 2, 97, close parentheses equals 215.2, p less than 0.001. So the values in parentheses again following the F are the regression and the residual degrees of freedom. So in multiple linear regression, the following formula can be used to compute degrees of freedom for the model's F-test. So again, we see, let's repeat that. So in multiple linear regression, the following formulas can be used to compute degrees of freedom for the model's F-test. So we have degrees of freedom residual equals K, degrees of freedom regression equals N minus K minus 1. So the degrees of freedom total is N minus 1. Or 99, there it is. So where K is the number of independent variables and N is your sample size. So in this example, we had 2 independent variables and it was 100 minus 1 to give us our total degrees of freedom. So again, we have our 2 and we have our 97, 100 minus 2 minus 1 equals 97. And then the N minus K would give you your 99. Or you can just add 97 plus 2. So many ways to get that. So with our coefficients table at the bottom, now we're on page 18 of 19. So that third table, as with our simple linear regression, we can ignore the row labeled M0, which is the null model. Okay, so that top row, that does not include any independent variables, okay? So we want to focus on M1. So we have our y-intercept and our slopes that are associated with our model, and they can be found in the column labeled unstandardized. So that's like the third column, unstandardized, okay? So our y-intercept is the 125.97, all right? And then the slope with Danny's sleep is that negative 8.950. And then the slope associated with the baby sleep is 0.011. You put that all together and you do the 125.966 plus the negative 8.950 plus the positive 0.011. All right, and you plug it all in. So the coefficient associated with Danny's sleep is quite large, right? Suggesting that every hour of sleep that Danny loses makes Danny a lot grumpier. However, the coefficient for the baby's sleep is small, which suggests that it really doesn't matter, how much sleep the baby is getting. So what does matter as far as grumpiness goes, right? Danny's grumpiness goes is how much sleep she gets. So to further investigate the statistical significance of each of the independent variables, we're going to look at the t-tests and their respective p-values. Those are the last columns, okay, in the table. So for Danny's sleep, the p-value is 0.001, okay, which tells us that this slope is significantly different from 0. And for baby's sleep, the p-value is 0.969, which is larger than the standard 0.05 alpha level. This tells us that the slope for baby sleep is not significantly different from 0. In practice, at this point, we'd probably remove baby sleep from this model, and we just use the simple linear regression model that we saw earlier with Danny's sleep as the only predictor variable. So we're moving into section 11.5.3, visualizing the multiple linear regression model. We're at the bottom of page 18. So with simple linear regression, we could create a scatter plot to display the data with one variable on the x-axis, one variable on the y. It does make perfect sense, but now that we have that third variable, how should we visualize the data? So with 3 interval or ratio variables, we can actually use the 3D plot to visualize the relationship. So while JASP does not generate this type of plot, this figure 11.15, it is really helpful in providing a sense of what a multiple regression model looks like by showing it is a 3D plot that includes all 3 variables along with the regression model itself. So again, that's at the bottom of page 18. And so to summarize, the multiple linear regression, it extends the principles of simple linear regression by incorporating multiple independent variables to better explain the variability in the dependent variable. So by understanding and applying the assumptions of multiple linear regression, we can build more robust models that provide deeper insights into complex relationships. So while the addition of multiple predictors can enhance the explanatory power of the models, it is crucial to remain vigilant about potential issues such as the multi-collinearity and to interpret R-squared and adjusted R-squared values very carefully. So we're on page 19, and we're going to look at section 11.5.4, which is the interaction effects. So this is just the last concept that this author would like us to review. They want to mention this before wrapping up the discussion on multiple linear regression. So again, it's called interaction effects. So while we are not going to be delving too deep into this concept. It is very likely that you would see interaction effects when you're reading published research studies that use regression methods. So in multiple linear regression, we have two or more predictor variables, okay? And we often want to know if they interact with one another in relation to the outcome variable. So this is known as your interaction effect, all right? This means that the relationship between the predictors and the outcome is not simply additive, but rather it's multiplicative. So in other words, the effect of one predictor variable on the outcome may depend on the value of another predictor variable. So let's continue with the parenthood data set. We're going to look at our example using Danny's sleep, baby's sleep, and prediction of grumpiness. We may be interested in knowing if there is an interaction between Danny's sleep and baby's sleep in predicting grumpiness. So mathematically, this is our what our regression model would look like with the interaction effect. So it's this complex equation. So it's y subscript I equals beta 0 plus beta 1 x subscript I1 plus beta 2 x I2 plus beta 3, and then you multiply xi1, xi2, and then you add the epsilon subscript I. So in this model, beta 3 is your slope for the interaction between the two predictor variables. Now consider this scenario where Danny's sleep and baby's sleep are both low. So in this case, Danny's grumpiness might be very high due to the combined lack of sleep. However, if Danny's sleep is high and baby's sleep is low, Danny's grumpiness might be moderate, indicating that Danny's sleep can somewhat mitigate the effect of the baby's sleep on their grumpiness. Conversely, if both Danny's sleep and baby's sleep are high, Danny's grumpiness might be low, showing that adequate sleep for both Danny and the baby leads to minimal grumpiness. So interaction effects are often very important when understanding complex relationships in psychological research. They allow researchers to explore how the different variables work together to influence your outcomes, and it provides a more nuanced view of your data. So let's go and summarize. So we just finished up with visualizing and interaction effects. So again, in this chapter 11, the author built on what we have learned in all of the previous chapters, right? So both Pearson's R and simple linear regression are used when with two interval or ratio level variables. Now, while Pearson's R provides information about the strength and the direction of the relationship between the two variables, the regression allows us to make predictions. So we learned how to use our statistical software to conduct a simple linear regression analysis. We learned how to check the 4 assumptions of simple linear regression. We have our acronym LINE: linearity, independence of errors, normality of residuals, equal error variances. While the majority of this chapter was focused on simple linear regression, there was an overview of multiple linear regression presented at the end. Multiple linear regression is an extension of simple linear regression. We also went over how to interpret R-squared and adjusted R-squared values and how to interpret our output, as well as how to examine the 3D scatter plot. All right, and that concludes chapter 11.